All right, so in this example, we'd like to compute the mass of a ball given by this equation, x squared plus y squared plus z squared less than or equal to rho squared, where here the rho is the radius of the ball. So that means that if we have a radius here, the length of this radius is the number rho. And we are given that its density is proportional to the distance from the z-axis at any point. So let's just stick with this point P, this point that I've drawn here, call it P. The density of the ball at this point is proportional to the distance from the z-axis. And of course, in cylindrical coordinates, the length of that distance, that's our r. Okay, so that means that our density function, which is also called rho usually, so this is a little confusing, but the density function in this case is going to be some constant times r, where r is the cylindrical coordinate of that point, so the radius in cylindrical coordinates. Okay, and as we know, the mass is equal to the triple integral over the entire ball of this density function, k times r dv. And so what we need to do is compute this integral of the density function over the entire ball. Again, k here is a constant, and r, though, is the cylindrical coordinate. Okay, if we're going to stick with cylindrical coordinates, we need to get everything in terms of cylindrical coordinates. And of course, the ball is not a function in cylindrical coordinates. So what we're going to do is we are going to maybe chop this ball in half. And again, because of the symmetry here, all we have to do is compute the mass of, say, the upper half of the ball and then double our answer. So that's what we're going to do, okay? So we'll say then half of our mass is equal to, I've sketched in the intersection with the plane, the ball with the plane. We'll call that region D, and then the function that gives us the surface of the upper half of the sphere here, that's going to be take this equation, solve it for z, where z is greater than or equal to 0. Okay, so our mass is given by double integral over the plane region D of, we'll write this as an iterated integral, the integral in the z direction from 0 up to this equation, and this equation is, of course, if we solve this for z, and remember that z is positive, this is the square root of rho squared minus x squared minus y squared. Then we have our density function, k times r. This is integrated with respect to z, and then with respect to the area element in the base after, in the second iterated integral. Okay, the inner integral does not depend on z, so this is just very straightforward. We end up with 1/2 mass is equal to double integral over the plane region D, that's a disk by the way, of k times r times this function. So k times r times square root rho squared minus x squared minus y squared dA. So that's just computing this integral with respect to z. At this point, we've already got the r here from our cylindrical coordinates, and we notice that the rest of this is going to be much easier to do in polar coordinates, right? Because when we project everything down here, we're just in the plane, we're in polar coordinates. And so, I mean, we could have done this from the beginning, we could have recognized this because we were thinking in cylindrical coordinates already. But the changes that we have to make are the following. This minus x squared minus y squared, that's going to be minus r squared. So the entire radicand underneath the root here becomes rho squared minus r squared. Rho is a constant, r is our variable. And of course, our area element in cylindrical or polar coordinates is r dr d theta. Okay, so we get an r here. We have an r from our density. We have this whole term underneath a root. So let's see what happens. So what we end up with is that 1/2 of the mass of this region is given by the double integral. The radius goes from 0 to rho, so that's going to be the inner integral here. R goes from 0 to rho. Theta goes all the way around the base, so this is 0 to 2 pi. And then we've got our constant k from our proportionality with the density up here. So there's k times r, so that's the proportional r, times another r. So r squared, square root, rho squared minus r squared, dr d theta. Okay, and so this is what we need to compute now. I'm just going to copy this to a new page to have some more room to actually do the work. All right. Well, we've got r squared here, dr. This is what we're computing, the inner integral first. By the way, this whole thing is separable. So what we can do is pull out the theta integral, and the k can go with it. And we can then write this whole thing as k times the integral from 0 to 2 pi, 1 d theta, times the integral from 0 to rho of r squared times the square root rho squared minus r squared dr. This whole thing right here is just 2k pi, and so this is to be computed. That's all we have left to do, is this single integral with respect to r. So let's do it. Integral 0 to rho, r squared, square root, rho squared minus r squared dr. This integral should be done by a trig sub, so what we can notice is this is rho squared minus r squared. So we can say, okay, let's let r equal rho times sine of theta. Why? Because then this integral, so rho squared minus r squared becomes, if we make this substitution, rho squared minus rho squared sine squared of theta, which is rho squared times 1 minus sine squared theta, which is, of course, cosine rho squared cosine squared theta. Okay, so that's going to be, we're going to have that there. Then, on the other hand, we need to always compute dr if we're going to do this. And so dr is going to be rho cosine of theta d theta. So that'll go in here. We've got this here, and then we're going to have to plug in here. We should also change our limits since we have them. So we need to solve for this, right? So this tells us, okay, sine of theta is equal to r over rho, which means then that theta is equal to the arcsine of r over rho. And so when r is equal to rho, arcsine of 1, that's going to be pi over 2. When r is equal to 0, arcsine of 0, that's just equal to 0. Okay, so we can transform our integral. It becomes integral from 0 to pi over 2 of r squared, that's going to be rho squared. I'm just going to go in order here. Rho squared sine squared theta times square root of all this, so that's going to be rho times cosine of theta, times dr, which is another rho cosine of theta d theta. And we group all this together. We take all these rho's out because rho is constant, and obviously we have to square this and do some trig formulas here, but this becomes rho to the fourth integral 0 to pi over 2. This whole thing becomes sine squared theta cosine squared theta d theta. And then let's remember how we deal with even powers of sine and cosine in an integral. So of course sine squared theta is equal to 1/2 minus 1/2 cosine of 2 theta, and cosine squared theta is equal to 1/2 plus 1/2 cosine of 2 theta. So if we multiply those together, what do we get? Cosine squared theta times sine squared theta, order doesn't matter here. This is going to be 1/4 minus 1/4 cosine squared 2 theta. Okay, and then we have to do another reduction on this one. And so this whole thing is going to be 1/4 minus 1/4 times 1/2 plus 1/2 cosine of 4 theta. And when we work all this out, we end up with a quarter minus 1/8. So that's going to be 1/8 minus 1/8 cosine of 4 theta. Okay, so this becomes the integrand. That's all trig sub, so we don't have to worry about the d theta. Those trig identity, I should say. So that everything here is equal. So what we end up with is this is rho to the fourth. The 1/8 can even come out. Integral from 0 to pi over 2, 1 minus cosine of 4 theta d theta. And now if we think about it, cosine of, so when this is 4 theta, pi over 2 goes in here, this is just 2 pi, so this whole term is 0. You should work that out, but that term's not going to contribute. And what we end up with for our mass of our ball is that the mass, half of the mass, remember this is just half of the mass, is equal to rho to the fourth over 8 times pi over 2. This integral is pi over 2. But at this point, we can't forget that we also had this term up here. The 2k pi came from the other portion of this double integral. And so at this point, what we have is that half of our mass is equal to 2 times k times pi. That's from the first portion of the integral up here, times this portion that we just finished, the TBC. So this is rho to the fourth over 8 times pi over 2. And of course, we're going to multiply through by 2. That'll cancel these. And what we learn is that the mass of our ball, I'll write it in red, mass of our ball is, this 2 can cancel with here and make this a 4. So what we end up with is the mass of our ball is k times pi squared times rho to the fourth all over 4. So this is the mass of the ball whose density function is proportional to the distance from the z-axis.